The speaker is Andries Steenkamp from CWI Amsterdam. He's one of the 15 doctoral grants of Poema. I think you are ER6, no? These are our labels. And he will speak about lower bounding complexity, positive matrix factorization rank for sparse matrices. Maybe you read better than I.
Right. Thank you for the introduction. Thank you to the organizers for inviting me. Even though it is medical ESR, it's always a fun experience. So I'll be talking about the completely positive rank of a matrix. I'll explain what that is. It's hard to compute, so we lower bound it. And we can lower bound it better if we have sparsity in the matrix, so 0 to the matrix. This is joint work with Sam Köbling, Björn Koda, Monique Laurent, and Victor Magron. And these two are from Toulouse, which is where I did my secondment, where a lot of this work comes from. So without further ado, let's jump into it. So what I have in store for you today, so you don't have any surprises, I will introduce a combinatorial parameter rank CP, because it will be hard to compute. So we have to have lower bounds. So I'll introduce a natural convexification, namely this parameter tau CP. This tau CP will it'll have a nice property that we can reformulate it as a GMP, generalized moment problem. I will explain what a GMP is when the time is appropriate. Having built a GMP, we'll then attack it using the standard Lasserre hierarchy. There'll be some techniques we'll show in between. And then we'll also see, okay, but if we have sparsity in the matrix, we can build an even stronger hierarchy, an equivalent GMP. So that is what's on the menu for today. So, step one, what is a completely positive rank of a matrix? You're given a n by n matrix, non-negative. The rank CP is the smallest integer r, such that you can find these factors a1 to ar, such that you can non-negative factors, length n, such that you can represent your matrix A in this symmetric factorization. Now, clearly, this does not hold for all matrices. Like if your matrix is not PSD, you're not going to be able to do that, for example. But even if it is entry-wise non-negative and PSD, you might still not be able to do that necessarily. But if you can find such an R, find such a factorization, then we call such a matrix completely positive. And we call the associated factors CP factors, completely positive factors. Right, that sorts the what we're interested in. Now for the why we're interested in. There are some sexy applications in quantum information theory, teleportation, quantum computing, cryptography, not my field of expertise. There are some nice applications in copositive optimization. This comes from the fact that the kernel of copositive matrices and the kernel of completely positive matrices are dual. And a lot of combinatorial problems can be reformulated as copositive optimization problems. So, interesting stuff. If you're a practically minded individual and you like statistics, there's an application called experimental block design. Not going to go into detail of that. And then lastly, CP matrix factorization rank is one of many matrix factorization ranks. So if you understand one, maybe you understand the others better. So maybe. Cool, so that's the why. Now, this combinatorial parameter is unfortunately hard to compute in general. Hence, we're motivated to find lower bounds for that we can compute. So first choice, we're going to introduce this tau CP parameter. We'll start by defining this convex hull of rank 1 matrices with the property that entry-wise non-negative, and they have to be entry-wise less than the entries of matrix A, and they have to be, as a whole, PSD less than matrix A. Then we define tau CP to be the smallest real number, non-negative real number, such as 1 over lambda times A belongs to this convex hull. So in other words, you can find a convex combination of convex combination of A with some scale. Okay, so why is this natural? Why is this a lower bound? Consider you do have a CP factorization given here, matrix A, and your CP factors a little al. Then just consider 1 over R of A. It has to be in this convex hull because you basically already have the convex factorization given to you from the CP factorization. So then that's your quick answer for why tau CP is a lower bound, the rank CP. Okay, so are we out of the woods yet? We just compute tau CP and then we have something? No, not quite. So there's no clear way to compute tau CP directly because that convex hull is a bit weird to characterize, and optimizing over it doesn't get easy. And even if we could compute it, it is a convexification of a combinatorial parameter. So there are examples where you have a strict inequality. And okay, I don't know of how big this gap can be between the convex parameter and the combinatorial. But there is a silver lining. Silver lining is we can reformulate tau CP as a GMP, and that will allow us to attack it using a hierarchy. The hierarchy steps will we be able to compute. Okay. So I guess 6 slides, 6 minutes. Small rest break. Any questions about the separable rank or the CP rank? There's not. Then we proceed. So a little bit of theory about GMBs, generalized moment problems. Generalized moment problem, I've written one here. It is an optimization problem over measures, Rn. You encode the data in terms of polynomials. So the objective is the integral of polynomial p0, u. Your constraints, again, the integral of polynomial pi, you have to fix it to a bi. And the support of your measure has to be contained in a semi-algebraic set. Okay, I've written one. So you have your polynomial inequalities, and you have your polynomial equalities you have to satisfy. Note, I have not written the equality constraints, the ideal constraints, in the most general form that they normally occur. I've written them specifically in the form of monomials, because that is the case that will be applicable to the sparse that I will be using for the CP factorization, for the CP rank bounding. So you have this expression for all little sets of the subs of in S, where S is now a set of subsets of N, so a set of 1 to N. S can be empty. You just don't have any sparsity to exploit in that case. All right. So that's a GMP. Clearly, first observation is your semi-algebraic set has to be contained in the variety generated by the ideal of the constraints inside the equality constraint. I mean, this kind of just follows from the definition. And since it's contained as ideal, we now start by defining first new objects of interest. These will be the inclusion-wise maximal subsets of 1 to n, such that none of these VKs contains an element of X. You can think of this as the biggest supports that you can have without containing any of your forbidden supports, or forbidden monomials, as defining your ID. And then using these maximal subsets, you can define a covering of K as follows. So KK hat is equal to all to X in K, such that the support of X is contained in VK. Notice this is now a lower dimensional part because the support of X cannot be full. It's constrained to VK. So K is now a union of these.
Excuse me, what do you mean by n is small?
Oh yeah, okay. I ignored the most important part. All right, so finding these maximal subsets is actually NP hard. But for our application, Rn is going to be pretty small, and it will be just so we can we can just use whatever algorithm we have to compute them, and that will make our life easier later on. But yeah, in true, you will later see that these maximal subsets will be like finding the maximal clicks of the graph.
So for typical application, n is about.
So like from 5 to 12.
Okay.
5 to 12 is a good range. I mean, yeah, the SDP start to kind of break before this thing breaks. All right. Yes.
Why are there many of those VPs and not just one?
Okay, so let's take, for example, let's say S contains only one set, like 1, 2, 3. Your N is 3, so you have x1, x2, x3, but you don't want the product x1, x2, x3, it's equal to 0. So that means one of these variables has to be 0. So your VP is going to be 1, 2, 2, 3, 1, 3. So yeah, it's. Wait, you repeat the question again. I had one of those moments. Oh, okay. Sorry, I got lost there. All right, so yeah, so it's basically breaking up the support into lower dimensional supports and then handling it there. All right, so we've broken up K, or we have a cover of K. Now, using this cover of K, we can now define a new GMP. Now, instead of having one measure we're optimizing over K many measures, one for each of these new Ks. Okay. So each one is supported on the, okay, so because these KK hats don't have full support, they're lower dimensional, so you go to the ambient real space, you go to your R to the VK, and you just project upwards. This GMP, we saw the vol ID before, now we see the vol SP, optimizing over K many measures. Instead of a single integral, we now have the sum of integrals. And because our polynomials come from, have n many variables, we now have to also restrict our polynomial to account for the support of the measure. Same with the constraints. Supports, measures now in these KKs, low dimensional. Note that in this process, we have actually encoded the ideal constraints into the supports of the measure. So they kind of disappear. We'll see. Right, so we have now have two GMPs. The question is, how do they compare? So we have our ID GMP, the dense GMP, and our sparse GMP, multiple measures. Just recording the definition, you can see how they're simple: one measure, multiple measures, one integral, sum of integrals, and then respective supports. So it turns out, okay, so I made a proposition. The two hierarchies are the same. So to prove this, you would do less than on one direction and greater than the other direction. I'll only do the more difficult side, but that's still pretty easy. So we'll prove that sparse GMP is less than dense GMP. Start with a single measure mu, solution to the dense GMP. We convert our covering of K into a partition of K simply by disjointification of the cover. So you just cleverly delete the overlap. And you end up with these sets lambda K. Now, having these lambda Ks, we use them now to define our measures mu K. Simply to be mu K is just defined to be our original measure E mu, restricted to the appropriate partition, K partition, and then we have to account for support of the function, because this function now has only like VK many variables, so you have to pad it with zeros appropriately to have a polynomial in Rn. Right, now why does this satisfy RSP? So the two conditions have been satisfied. So first, support, is support correct? We just take, we integrate over the supposed support we want to prove, RF, d mu. We encode the domain of integration in terms of an indicator function. We just apply the definition, expand out. We observe that the indicator function has to be 1 on this domain, so it drops away, and then we just apply the definition again. Because this, that, which is equivalent to sameness support. Objective values and constraints. To prove that, we need to prove this for any polynomial. We do both f and mu. Start with it. Clearly, because f is a solution to a dense, GMP support has to be contained in K. K can be partitioned by the lambda Ks. Just observe that the supports of, well, just observe that the supports of the x's for each lambda K have zeros in certain places, so we can just write it out in terms of padding out by zeros, and then just apply the definition and end up where we want. Good, yes.
So is this like a dual approach to further extension of further decomposition?
It's quite similar, but there's no need for caudality.
Yeah, that was my question.
Yeah, so the usual way we would go is you look at the matrix, you see, you find out the support graph is caudal, and you use Agler's result or its dual one. Yes. No, you don't need that. So. Cool. So that proves the one equality. The other side is even easier. So while ID is less than while SP, for that you start with your measures mu1 to mu p, and you just sum them together. Well, and then account for supports where it is appropriate. And that's how you get your measure solution for vowel ID. Cool. So, sorry, I shouldn't say cool. That concludes the GMP part. So any questions about GMPs before I go on to the moment method in a nutshell? All right. So how are we going to build a hierarchy? We've now built a GMP. So the usual approach is we take a measure. So I suppose many people in the audience are familiar with this. So if I don't hear enough grunts, I'll go slow through it. And if I hear a lot of grunts, I'll just go quicker. Given a measure mu, you now go to linear functional, echelon polynomials, defined on polynomial simply by the integral polynomial with respect to measure. That solves some of the constraints on the objective. Now, how do you encode support? You have your polynomial inequalities, polynomial equalities. They go to your quadratic modules. L has to be non-negative on the quadratic module, and L has to be 0 on the ideal generated by these expressions. That's written here, and in red I have just indicated the truncating of the degree. So you actually end up with something you can feed into the machine and can punch some numbers to get some concrete, tangible results. Right, so we apply this, and we can build our hierarchies. The two hierarchies that we can build is now obviously this one comes from the dense hierarchy, and this one comes from the sparse hierarchy. I put them side by side so you can compare them line by line. First obvious observation, one linear functional, then there is P many linear functionals, each of their restricted supports in the VKs. You have your constraints again, sum of constraints. You have non-negativity on the quadratic module, you have non-negativity on the restricted quadratic module, which is the support quadratic module. You have ideal constraints, you have no ideal constraints. So this is important. The ideal constraints are absorbed into the VKs, into the LKs in terms of their supports. And then just to recall what the quadratic module and the ideal is, how they're defined. Okay, now we've built two hierarchies. How do they compare? Are they equal? Is one better? Well, here's a lemma. The dense hierarchy, or the sparse hierarchy, XI is at least as good as the dense hierarchy. A quick way to see it, let's do the proof sketch. Let's say you have a solution L1 to LP of your sparse hierarchy. Then you can define the possible solution L for your dense hierarchy by simply summing together the little LKs. Again, you have to account for the support of the LKs because L operates on polynomials in n variables, and these LKs operate each respectively polynomials in dk many variables. By construction of PI, polynomial PI, you can just run through its definition, you get your PI. For something from the quadratic module, you just run through it, and then each of these terms is then non-negative also by the definition of the LKs. For the ideal constraints, something from the ideal, plug it into L, you break it into some, and then these things become zero, not because of ideal constraints on the LKs, but simply because something from the ideal is not supported by any one of the LKs, of the multiple LKs. So that's how the ideal constraint is transferred into the definition of the LKs. All right, no, we've built hierarchy. We've built two hierarchies. We've shown one is better than the other. Do they converge? The obvious question. And the answer is yes. It's a very classical result. You can read it up from Marcel's book, put it at the bottom. If we have an Archimedean quadratic module, yes, I have enough time. I think everyone is familiar with what Archimedean is. Well, I guess I'll write it out. 1 n squared. You need this thing to be contained. You need that polynomial to be contained in your quadratic module for some positive r, which is our case. I will point out why it is our case when we reach that point. So if you have an Archimedean quadratic module, your hierarchy does converge. Yes, so you see it's higher. Moreover, if you can find scalars z0 to zn, such that this polynomial expression is positive on your semi-algebraic set K, then you also know that the solution of your GMP has a finite atomic optimal solution, and that like the last step of the infinite step of your hierarchy is equal to a full GMP, the non-trivial one. Now, I only show this for like the dense flavor of the hierarchies and GMP, but the same holds for the sparse, because obviously the sparse hierarchy is lower than the dense hierarchy, so convergence follows. But you can also do it just from this result directly. Now, that concludes the general GMP moment method approach. Any questions before I show you how tau CP can be massaged into a GMP? All right. So we now go to return to our tau CP. Just recall the definition. We're trying to minimize lambdas such that A is equal to lambda times the convex combination of factors AL transpose, where these ALs come from the special set K. Special set algebraic, semi-algebraic set. Again, non-negativity, NGY is less than A, and P is A less than A. We go from this convex whole formulation of tau CP to a GMP by replacing convex combination constraint with a probability measure, first of all. And then, well, it's going to be a probability measure times this lambda. So you just absorb the lambda into the probability measure, and you end up with just a measure. So you end up with the following expression. Again, so you see the lambda becomes this integral. This constraint is there. The support makes sense. It has conditions K. The only odd one out is this mu has to have finite atomic support. So what does it mean for a measure to have finite atomic support? Simply put, you can write mu as as a sum of Dirac delta measures, where the support of each Dirac delta is contained in the set K. Well, okay, that doesn't apply to the support of that. Yeah. So intuition for why is this gap, or why is this jump? The intuition is you take a solution from tau CP, and you have convex scalarized convex combination of A, terms of elements of A, and you build your measure just as follows, just using the factors. Okay, now to get rid of the finite atomic support, you can invoke like a classical result from GMP theory. If asked, I will elaborate. If not, then don't worry too much about it, but simply put, we can drop it without consequence. I end up with this clean GMP. We're going to now start to get. Oh, that's a question. Right. So it's a clean GMP and our semi-algebraic set K, over which is defined. So this is already something which we can kind of attack with our hierarchy, but we're going to massage our semi-algebraic set a bit because I have foreknowledge of how it will feature in the resulting quadratic modules. So there's our set K definition. You can also use this equivalent reformulation with some polynomial identities which allow you to show that the quadratic module based on these inequalities will imply those. And because of that, because we know, well, I know beforehand that the quadratic module is stronger for this set, we prefer this one. That's the first reformulation. And the second reformulation, we're going to split this line into multiple lines, here in red, because we're going to take into account zeros in the matrix. This is where our sparsity comes in, and we will be creating ideal constraints. So let E subscript A is essentially the edges of the support graph of A. And where it's not supported, we get our XI, XJ, and Z. This is what our quadratic module becomes. Everything looks kind of, we can feed this into our GMP framework, which we saw a while back, except maybe this constraint. This looks a bit weird. It's not just a scalar polynomial inequality. Oh, yes.
Okay, so I'm sorry, this is, I just tell us how can an entry of a completely positive matrix be zero?
Okay, entry of a completely positive matrix be zero.
So because you're saying it's the sum of V transpose, where V is entry-wise non-negative.
Yes.
Right. So doesn't it? So how, if the entry is zero, doesn't it mean that the corresponding entries of all the V's have to be zero?
Exactly. The support is limited by the fact that there are zeros inside the matrix, and you have only non-negative terms that you can add together, so nothing can cancel.
But I mean, that doesn't mean that you can. Doesn't it make like the row and the column of matrices?
Not the whole and row of columns, because you have multiple of these factors you can add up. So some can fill in the patches where the others cannot. In fact, these V's are the supports, the possible supports of your factors. These V1 to VPs, they are the maximal supports that these factors can have. Yes, a common theme I've noticed in some. So we will see an example of a CP matrix and how you define the VKs and supports shortly. So there's our K, we've massaged it into this form. The last step is now the very last PSD constraint. Let's massage that. So first intuitive idea is we convert PSD of this matrix polynomial into non-negativity of its principal minus. You get it back to scalar inequalities, scalar positivity constraints. Then you have to do some symbolic computations of these polynomials px. You're into that. Equivalently, you can just do scalarization via these polynomials, where you take your V to be from the unit sphere. Again, now there's infinitely many of them, but in practice, you can just take an epsilon net. This was done by my predecessors in 2019. One of our contributions is we have a stronger constraint, which is this. Instead of having a scalar constraint for localizing, we have a matrix localizing constraint. Scalar localizing constraint, matrix localizing constraint. And this turns out to be strictly stronger than these two. So, okay, why massage it like this? Well, we get better bounds by encoding more constraints more cheaply. Now, everything we apply, we now have everything, we can massage it into a hierarchy. Don't freak out, it's a lot. I will break it into pieces that can be digested. Integrate over your linear functionals, your second order moments is determined by your matrix A. You have your three positivity conditions. Moment matrix has to be PSD, localizing matrices have to be PSD. We have ideal constraints for the non-edges, and we have our tensor constraint that we saw on the previous slide. And this is exactly what we punch into the machine to punch numbers out. Okay. Little bit of intuition just to solidate the idea that all hierarchy is just built to filter out linear functions which don't have the properties we want. So the linear functions that have properties that we want is given we have a CP factorization of a CP matrix A as follows. We can define evaluation functionals L of subscript A little l. Simply, this linear function just takes a polynomial and evaluates it at the point AL, which is in that set K. You just define L to be the summation of all these evaluation functionals, and then you observe it has all these nice properties that we want. So, I guess the only one here worth talking about is this last one, our weird tensor constraint. It's obviously then PSD because you plug in your AL to end up with a PSD matrix, PSD by definition, tensor product, PSD matrix. You have PSDs. Pretty much straightforward. So that whole hierarchy we've built is just every constraint has the intention of slicing out a linear functional which doesn't have the similarities to this function we've constructed. That's the intuition. All right. Now, so far I've only shown you the dense hierarchy. It's talked extensively about now. Where does this sparsity come in? So the sparsity, although zero entries in the matrix. So here's a concrete example. So this is a matrix which may or may not be CP. It has zeros. It doesn't have like a very clear pattern of zeros. If there were like two disjoint blocks, then you can break that into two CP matrix problems. But we don't have a clear example of that. So the matrix, define its support graph. So you get edges. So you have an edge between, like, this is 5 and 3. If 5 and 3 is non-zero, and more importantly, you have non-edges if you have a zero. And these non-edges are going to become what defines our ideal. So that was our S from the previous slide, or from a few slides back, just the non-edges of the graph. And then our V's are exactly the maximum clicks of the support graph. Here I've highlighted the big one. So essentially, our CP factors, their support has to be contained in one of these V's. It cannot be bigger than this because then obviously you have a zero entry in the matrix which shouldn't be there. All right, so that was the small example. So just recall the general formulation. We define the edges of the matrix. We define our V1 to VP, which are the maximum clicks in this case. NP hard to compute, but N is small. There's our semi-algebraic set K. We punch, well, we go through the whole process of defining the GMP and respective hierarchy. This looks even scarier than the previous one, but I'll walk you through it again. Instead of a single linear functional L, we now have multiple linear functionals, and they all have their restricted supports VK. Sum up, everything is pretty much quite clear. Maybe here at the tensor constraint, we have now this XX transpose. You truncate it to be, or you set all the xi's which are not supported by VK to 0. So it's still an n by n matrix, but it's padded by zeros where not supported by the VK. That's a sparse hierarchy. Multiple measures, multiple pseudo measures, but it's still something you can compute. All right, so I've convinced you theoretically that the dense hierarchy is, well, the sparse hierarchy is at least as good as the dense hierarchy. Now let me show you examples exactly how good or how big the separation can be. Consider the following CP matrix Bn, which is 2 by 2 block matrix. On the diagonal blocks, you have n+1 times the identity matrix. The off diagonal blocks, you just have all ones matrix. And the support graph is the complete bipartite support graph, complete bipartite graph. For this graph, level 1 of our sparse hierarchy applied to this matrix is at least m squared. Right. I made a typo here, it's not an A, it's a BM, so all coordinations BM. So XY event is larger than CFRAC. I haven't explained CFRAC yet. CFRAC is the fractional version of the click edge cover of a graph. So the click edge cover is like the minimal number of clicks that you require in order to cover every edge in the graph. And the fractional version is basically you write the IP and then you just restrict the integer restraint. And that is m squared. It's one for every edge. The dense hierarchy is bounded by m plus 1. And the way we do this is simply we find an explicit example, something that is feasible for the dense hierarchy. We plug it in, we see what it gets, and because the dense hierarchy is an infimum, so it has to be below our feasible suggestion solution. And the solution we suggest is this matrix, so it's scalar in the top left corner, a vector consisting only of square root m plus 1, and the matrix Bm, so not A, Bm. It's a bit technical, but you just massage it, show it's feasible, and this expression is less than n plus 1, easy comparison. So in summary, the sparse hierarchy can do quite a lot better than the dense one. Of course, if you have sparsity to explore. Now that handles the bound. Now, what about time? Usually sparsity is for time. Here I'm on time. All right, 36. So I'll show you a plot. Y-axis is time. This is 1 second. I think this is 100 seconds. On the x-axis, I have both matrix size and a quantity I call non-zero density. So non-zero density is like the number of non-zero entries above the diagonal divided by the possible number of entries that you can set to zero. So if your non-zero density is 1, you have a dense matrix. And I don't start from zero density because I need my support graph to be at least connected. Otherwise, I can break it up into 2 CP matrices and then factorize them respectively, or attack them. Here we go. This segment here is matrices of size 5 by 5. Nothing much of interest. 6 by 6 here, 7 by 7 here. Oh, the most important one. Red is the dense hierarchy. Yellow is the sparse hierarchy. Green, I will explain afterwards.
Green looks the best, no? So
green is actually a weakening of the sparse hierarchy. The sparse hierarchy, and then we weaken. Unfortunately, there isn't. We don't have that the weak hierarchy is comparable to the dense hierarchy. Otherwise, I would have some result.
So the technique you gave, you explained up to now is the yellow one, if I understand.
So
I'm a bit confused.
This is yellow. That's the sparse one.
Okay.
This is red. This is the dense hierarchy. So this is one that we want to take, one we suspect should take longer because it doesn't exploit zeros.
Yes.
And this one should be quicker.
Mm-hmm.
All right. So now, and there are multiple points per vertical line because even though non-zero density, you can have multiple graphs with the same non-zero density. So I didn't want to enumerate all graphs which are multiple certain sizes. That's that. So I just did it by the numbers. You see the red takes longer than the sparse as we increase the size and starts breaking away. Yeah, this is a log plot, so log axis. We have more sparse and something called the weak sparse, which I'll elaborate if we have time. And the gap just widens as your matrix increases and your sparsity is there to exploit. That is level 2 of the hierarchy. So that's XI SP2 and XI ID2. Level 3, it becomes more pronounced. 1 second, 10 seconds, 100, 1,000 seconds. Dense hierarchy climbs, and then I start making a cutoff. Sparse hierarchy, okay, so again, 5 by 5 matrices, 6 by 6 matrices, 7 by 7, and obviously the gap starts becoming more and more pronounced in the computation times. So, in conclusion, with these 2 slides, the sparse hierarchy is quicker to compute. Well, we have to compute if you have zeros, because obviously when your matrix becomes dense, then you have to start paying for the overhead of finding these multiple measures and defining a multiple measure GMP, because it's not worth it if your measures if they overlap heavily. All right. Conclusions. We've seen this rank CP parameter. We've lower bounded by a convexification tau CP parameter. We've written it as a GMP. The GMP has a sparse and a dense flavor, both of which, and we've shown that they're equal, both of which we can build a hierarchy for, but the sparse hierarchy is at least as good as the dense hierarchy. And I think those are my references. Hopefully we'll have something on archive soon for you to read if you wish. And I guess that concludes it. Thank you.
Thanks and congratulations, because all this CP stuff is well known to be hard. Bernard?
So in the usual CP problem, there's a phase transition 4 to 5. So 4 by 4 is very easy, 5 by 5 is complex. My question is, how do you see this? For example, if you have a sparse pattern where the clicks are size at most 4, do you get immediate tightness?
Yeah, I have actually not worked it back to that case, because I know like size 4 by 4 CP is equivalent to non-negativity, right? Or non-negative and PSD.
Here's my question. If your sparsity graph has small clicks in the sense,
Small clicks.
size at most.
I think maybe not, because I think you can stitch together a bunch of 4 by 4 clicks or size 4 clicks and still end up with like a monster. Maybe, let me just check my last example. It says bonus slide, cut content. This is a, this monster was constructed specifically to have high CP rank. So let's just quickly see. I think this one has click size 4, so it's a tripartite graph. So there's one part, the other part is 4, 4.
So T is 6.
Sorry, what was the question?
What is T here?
T.
Yeah.
So T is level of the hierarchy. So we haven't. Okay. So I've only computed T. T is here, like 1, 2, 3. But yeah, this is just the matrix. It has 64 maximal clicks. I guess that those are triangles. Yeah. So then the triangles. Your rank is 10. Your click cover. So so your click edge cover. The minimum number of clicks you need to cover all edges. That's 16. Nice proof for that. Rank CP is 37 for your creator. Level 1 of our dense hierarchy gives 4.85. That sucks. Level 1. Okay, I probably should say that. Yeah. XI1 of SP says that the sparse hierarchy hits it at a 29, and then it kind of looks like it stays at this 29 region. But since I have the time to spare, I might as well tell you what this weak sparse hierarchy is. So essentially, this is now your sparse hierarchy. The weak sparse hierarchy is, instead of taking this matrix as is, you truncate it only to the principal, to the minor supported by this VK. So you end up with a VK by VK matrix instead of the n by n matrix. They are not equivalent. So you end up with a strictly weaker hierarchy. But this is the bottleneck. This is our biggest PSD constraint, and this is the one that the computer complains about first. So by weakening it, we end up with this separation between the green and the yellow, the weak sparse.
There was another.
Yeah, at some point you get different definitions of the same semi-algebraic set. If I understand correctly,
So why is the quadratic module stronger if I start some case? Right, so just recall, these are various K formulations, the quantities, and at the very end, let's see if I have bonus slide. There we go. So I'm using these polynomial inequalities filtered from another paper. So essentially, we start out with something like this: xi is non-negative and AI, yeah, AIJ minus XIJ, these types of things. Let's see. They're containing expressions like this, where now we have like the square root of AI. So it's basically using this. Yes. So you can see with the inclusions. All right.
Maybe Marcus was.
You defined this general framework first for sparse GLP. Then you applied it to the same problem, but can you apply it to other problems with natural sparsity?
Yes. Like, okay, so this is actually what we're still kind of working on. So yes, we have this general framework. We apply it for the CP rank, but I think you can also have like a polynomial optimization problem where you want to have, if you happen to have those type of ideal constraints, then you can get away with it. You can also get away with it if you can massage those ideal constraints via a change of variables. So in short, it's still an active investigation to find out more places where we can apply this hammer. Yes.
Greg, please.
Yeah, are there techniques to construct matrices with high CP rank? Like you gave this 37.
Yes, this thing was specifically constructed, and this is, I think, from Bomser, Schlager, Ulrich. I forget all the authors, but there's like four authors, and there's like 2 papers on like constructing matrices of high CP rank. These matrices were constructed specifically to break a certain conjecture, which was like the CP rank is bounded above by like n squared divided by 4, which is like the CP rank of these bipartite matrices. So people used to think this was the highest CP rank you can build, but that has been disproven. So they have techniques to build these matrices.
I see. And so how far away can we, I mean, like, so there is a carry theory now, right? You can just, you can just say, because, you know, I mean, you're taking a convex hull, so,
yeah.
So the maximum is bounded by the dimension. And how close to the dimension can we get via constructions?
I don't really know. That's not, well, it's quite technical building these matrices, so I haven't like familiarized myself with the technique, but I can maybe offer another insight. From the numerical exercises, I can see that these high CP rank matrices seem to be quite rare. So they're probably like some extremal points in the code, I guess. But
well, no, I mean, they have to be kind of, they have to be a full dimensional set, but I mean, that's just not like from general convexity, but beyond that, they could be very small high dimensional.
Yeah, so let me rephrase that as like, by random chance, I missed them almost every time.
Marcus,
You always assume that your given matrix is complete.
Yeah.
In practice, the difficult problem is to find out if a given matrix is complete. So, could you use this technique? Of course, if it is, then you will find it.
Yeah. So I'm glad you asked, because that is what we do. I haven't shown it yet. So we have examples of matrices which are PSD, non-negative, but not CP. You feed them into the hierarchy. And if your hierarchy spits out a infeasibility certificate at a certain level, that is your certificate that this thing cannot be CP, because the CP matrix would satisfy those conditions. So yeah, you can test CP membership.
Okay, so we thank Andries again.